So using conventional cytogenetics, I'll just give you an example of copy number. So you can paint chromosomes and give them each a color so you can identify which number of chromosome it is. And this is a normal situation. Everybody has 2 copies of the chromosome. Well, this is a cancer patient, and you can see that, for example, on chromosome 3, there's an extra copy, and in chromosome 17, there's a loss of a copy and some other things. You can also see that there are different colors here, so pieces of other chromosomes stick to other chromosomes, and Dr. Kyle has already mentioned the importance of this, where he's talked about 17 deletions and translocations. So these are very, very important contributions to myeloma. Well, genomics has really revolutionized the way we study DNA. I'm going to talk to you from here on in about some of the specifics. So we have extremely mind-boggling technologies that allow us to look at DNA and RNA in a very, very sophisticated and high-resolution way. So instead of looking at the painted chromosomes like you saw, we have the resolution that we've never had before, and it's really, really impressive, where you can assay and survey every single gene in the body in one experiment using a chip, which if you go to the TGen booth, they're out there. So this is just an example of a gene chip which allows you to survey some of these changes in one shot. So it's and then these are just images of some of the software, some of the equipment that is used. So essentially, we take human specimens and we interrogate them using these genomics capabilities, and it gives us readouts of this sort. And these readouts, and deciphering what these readouts are across multiple groups of patients, can help us lead to better diagnostics and therapeutics. So from this, we've gone to these high-resolution images, and this is actually from a study that was in collaboration with TGen and the Mayo Clinic here in Arizona, where an identification using some of these so this is a copy number study way back when. This is copy number analysis now. This is the difference. This is what it looks like on the screen. This is how we look for copy number changes. And here we see that this important deletion in a very, very important gene occurs in a high frequency of myeloma patients. And proteins that belong to this sort of group of molecules abnormalities in this group of proteins occurs in about 50% of myeloma patients. And so we've also shown that patients who have these abnormalities can respond better or worse to certain treatments. So these are some of the things that are being used to basically better stratify patients into different treatment options. So this study was a good segue into the Multiple Myeloma Research Consortium Genomics Initiative, which is a comprehensive genomic analysis program that was designed to rapidly accelerate progress made against multiple myeloma by significantly improving and understanding the biology of the disease. And this was a collaboration with many, many institutes across the country. The Multiple Myeloma Research Foundation and the Multiple Myeloma Research Consortium funded the study, and it was a collaboration with TGen, the Broad Institute, the Mayo Clinic, and the Dana-Farber. And I have to say that myeloma is actually becoming one of the best characterized cancers that do exist, because we now have the kind of data that none of the other cancers really have. And so the reason why that is because so there's data available for all of the different mechanisms in other cancers, but we have all of that information for the same group of patients. So this study basically started in 2005, and it just closed in 2009. And 250 newly diagnosed patients with myeloma were included in the study from 15 different institutions across the country, for which gene copy analysis was conducted, gene expression analysis was conducted, sequencing analysis was conducted. And now all the study is available, and the beauty of this is it's available to the entire world. So it's in a public portal for anybody across the world who's doing myeloma research to access and look at the data and try to interpret it. So it wasn't just for our use. This, of course, requires comprehensive bioinformatics analysis to really search for these new targets. But DNA is really not that simple. It's not as simple as losing or gaining copies. It's not as simple as mutating a gene, and it's not as simple as turning on or off a gene. it's really a lot more complex than that. So if you look at the simple sort of description of DNA, I should mention that just before I move on to this, with the Genomics Initiative, the study has been complete. So essentially what that means is the data has been generated. So I think that's an important point. We're now analyzing the data. So there are studies that are now being reported at the conferences. So several were reported at ASH this year. But the data analysis phase is probably more difficult than the data generation phase. So this is where we are at this point with the Genomics Initiative, is we're in the data analysis phase, and there will be papers that will be coming out in the next year or so, and then forever after that, that have basically been the result of the Genomics Initiative studies. So you can see that DNA, as I was saying, is not that simple. It wraps around proteins. It coils up in all kinds of ways that basically give you that shape of the chromosome that we all see. So in addition to the changes that occur at the sequence level, the expression level, the copy number level, you can imagine that with this kind of complexity, there are changes that happen over top the DNA. So structural changes can occur to the DNA. So in addition to these genetic heritable traits that we acquire and we've talked about, and I've showed you some of the data that, some of the studies and things that we're doing with that, there's a whole other field called epigenetics. And they're also heritable traits, but they don't involve a sequence variation in the DNA. And there are several of these. And where my study comes in was really to study epigenomics and myeloma, is to really, the one part of the Genomics Initiative that was not covered was epigenomics. And so the epigenomics study that we're now conducting at TGen in Dr. John Carpton's lab in collaboration with the Mayo Clinic is to really explore this next element. So as I was just saying, you can see the coils or all kinds of modifications that occur, and these modifications are just as critical as these genetic modifications that we've talked about, and we need to be mapped. And it's basically going to be the full picture that's really going to give us the answers that we need. So just a little bit of a slide that was presented at ASH at this year's meeting was a study that I'm working on, as I said, in epigenomics. And just to give you a little bit, so often we want to identify patients who are not going to do well. So we look for the high-risk group. Well, what about the good risk groups? So this epigenomics profiling study that we conducted may have identified a group of patients that may actually do better. So you can identify them using epigenomics biomarkers to say, well, this patient we know has this epigenetic change or doesn't have this epigenetic change and may actually do better than some of the other patients. So we're now, this is still very, very early phases of this work. It is in publication right now, but we're working on further characterizing this possibility. And with that, I'd like to end and acknowledge some of the people who are critical to this work. John Carpton, my mentor at TGen, Angela Baker, who was very important to the myeloma, the MMRC Genomics Initiative in John's lab, and then all the people at the Mayo Clinic who really were great to work with: Raphael, Greg, Leaf, Jonathan, Bumi, and Danielle Clare from the MMRC and the MMRF. And with that, I'd like to say thank you.